and I'm following the syllabus as it is given to us by the department. Summary of the real number system. So we ought to know natural numbers, and natural numbers are positive. Counting numbers starting from 1, whole numbers are also counting numbers starting from 0. Integers, positive or negative whole numbers, including 0. Rational numbers. What is a rational number? A rational number is any number that can be expressed in the form a over b, where a and b are both integers. Remember, the z stands for integers, but b is not equal to 0. Okay, remember that if b is equal to 0, then it means that the expression is undefined. Okay, whole numbers and integers, proper fractions, improper fractions, and mixed numbers, terminating decimals, recurring decimals. So that's all the things that we need to take note of. What is an irrational number? An irrational number, and as I said, you will have all of these notes. I sent it to you already, and if you send me your email address on WhatsApp, then I will email it to you. An irrational number is a non-terminating or a non-recurring decimal. And also remember that what is a non-terminating decimal? It means that it does not stop. And non-recurring means it doesn't have a dot on top of the number. Non-terminating means that after the decimal, remember decimal will contain comma, but in that decimal you would have a dot, dot, dot at the end. Now, here the square root of a negative number, or the square root or the even root of a negative number is going to be an irrational number. Now that is classified as a surd. A surd is an imperfect root. So it's not a perfect root, then that's the definition of a surd. Another classic example of irrational number is pi. Now remember, pi is going to be the circumference of a circle, meaning the perimeter of the circle over its diameter. We roughly get 3,1412, and that would be a non-recurring decimal because you'd have lots of decimals that follow that. You cannot express an irrational number as a fraction, and that's important. Real numbers, any number on a number line, all rational and irrational numbers put together. Calculations that do not produce real numbers. Square roots of a negative number is non-real, and division by 0 is undefined. A surd is a root of an integer that we cannot express as a fraction. Now remember, when I say integer, the root of an integer, it's not actually the root of an integer, but rather the root of a natural number, because you can't have the root of a negative number or the even root of a negative number. But having said that, you can have the odd root of a negative number. Give you an example. The cube root of minus 27 is minus 3. So see what happens when you put that in your calculator very quickly, right? Let's do that. Let's put that in our calculator. Example, the square root of 2. Now we know that is a surd. And then you press equal to, and then we look at the decimals. See, that's now going to be a non-recurring and non-terminating decimal. If you put pi equals to decimal 3,1415, so on and so forth, right? So that's why I said 1415, but it's just going to be also a non-recurring, non-terminating decimal. See what happens when you put the square root, let's say, of minus 4. So that's the square root of a negative number. That should return an error. Now you're not going to write error in your test or exam. You'll write non-real or unreal. Okay. Similarly, if you divide by 0, any division by 0 is undefined. So that calculator should return a 0. Let's say we put 5 over 0. That should return an error. But our solution to that would be undefined. But what if your numerator is 0? When your numerator is 0, so long as your denominator is not 0, it can be anything. Let's put 5, 0 over 5. And this should return 0. Therefore, that will be 0. Let's look at the odd root of a negative number. Odd root meaning a cube root. Let's say cube root of minus 27. So that's the cube root, but it's an odd root of a negative number. Now that should return negative 3, which means that it is going to be real. Negative 3 we know is an integer, and it's also rational. So minus 3. So this is the theory that we ought to do. Examples of surds are root 3 and root 2. Rounding off the number after the cutoff point is 4 or less, then we leave the number before it as it is. And one of the things that we ought to do as well is rounding off. So looking at that, they're saying that if the number is equal to 5 or more, then we increase the value of the number before it by 1. Okay, so rounding off is in our syllabus as well. So let's look at the following examples. But before I look at these examples, it says state whether the following numbers are rational or irrational or neither. So we have a whole array of examples, and you can just take down the solutions because you are going to get this material which you can print or keep a PDF of the complex number system, and it looks like this. So we can say complex numbers, it's like that, complex numbers, and complex numbers are separate into real numbers, and the symbol for real numbers is a R, which looks like that, and non-real, which looks like so, non-real. So that this, see when I say not in maths, this means here, that means not real. The R stands for real. Okay. Then moving on further with our tree diagram, the definition says that real numbers consist of all rational, which is the symbol is Q. Rational, you can take this down, and all irrational numbers. And irrational is not Q, like so. Now, as I've already discussed with you in the notes that I've sent you, okay, so you should get a PDF of this notes here. You look at the definitions and we can go over it again just now. We'll just go over it very quickly. Now, under rational numbers, we'll have natural numbers. And the symbol for natural numbers is a capital N. Whole numbers. And the symbol there is NO, or N subscript O. And then we also have integers. And that's a symbol for integers is a Z. So if you look at it now, we are able to classify all our numbers. Complex numbers consist of all real and non-real numbers. The symbol for real numbers is a R, for non-real numbers is not R. Remember that complement on top there, that little dash on top means not. Rational, the symbol is a Q for rational, and for irrational, the symbol is not Q, that's irrational. Natural numbers, remember, symbol is N, for whole numbers it's NO, for integers it's Z. So this diagram is kind of neat because all natural, whole, and integers are rational numbers, and all rational numbers are real. So we can classify a specific number into more than one category. So if you have a number like 2, for example, 2 would fall into the following categories. It's a natural number, it's a whole number, it's also an integer, and it is a rational number, so it's Q, and it's also real. Let's say you had a number like, for example, 1, or okay, let's say minus 2. Now minus 2 is only an integer. It's not a whole number, neither is it natural, but it's an integer, it's rational, and it will be also real. Okay, let's say if I had a number like half. Now half would only be, remember, rational and real because it's a fraction. That will be rational is Q, and R is for real. Let's say I had a number like pi, or I was given a value of pi. Pi is just irrational, and it will also be real. Let's say I had an example like, for example, 2 over 0. That one there will be undefined because we have division by 0. Let's say I had the square root of minus 2. That one there will be non-real. So these are all of the symbols and the theory that we must be able to put into practice. Okay? Right, so this particular diagram is important for you to be able to understand, and it makes you understand the whole number system. So once again, complex numbers consists of all real and non-real numbers. Real numbers consist of all rational and irrational numbers. A rational number is any number that can be expressed as a fraction, where a and b, if I have a over b, a and b are both integers, but b can't equal to 0 because division by 0 is undefined. Irrational numbers is any non-recurring or non-terminating number. Example is surd, so an imperfect root is irrational. And a classic example of irrational is pi. All natural, whole, and integer numbers are rational. So those are the examples. Right, so back to our module. Got A 0.25. So A, they only want us to say whether it's rational, irrational, or neither. So the first one will be rational, that's A. B will also be rational. C, because you've got a rational, rather irrational plus a rational number, pi, remember, is irrational. So therefore, that will be irrational. D, the square root of 10, that is a surd. Therefore, that's also going to be irrational. E, the square root of minus 16, we can say neither. But remember, if we want to go further, we'll say, why is it neither? Because it's non-real. Because it's the even root of a negative number. F, the square root of 16 equals to 4. Therefore, that's rational because you can see that will be a natural number, it will be a whole number, and it will be an integer. Okay, therefore it will be rational. G will be rational number, that's an integer. 0 is an integer. H is neither because division by 0 is undefined. And I, now you can see this here after the decimal, this dot, dot, dot. That means it's non-terminating. That means it continues. So if it's a non-terminating decimal, that one there is simply irrational. J, once again, that's a non-terminating decimal, so that's going to be irrational. The cube root of minus 27, I've discussed this one already, is going to equal to minus 3. When in doubt, we can just use our calculator. They have already got it here. The cube root of minus 27 is minus 3. That's an integer, so therefore we can write down rational. And the cube root of minus 9. Later, double check. We can say the cube root of minus 9 equals to. Right, so that's not a perfect, it's not a perfect, which makes it irrational. And then n, now the square root of 9 over 16, the square root of 9 over 16, there's a working here. Square root of 9 over 16 will equals to, now according to the third laws, it'll be the square root of 9 over the square root of 16, which is 3 over 4. That is a rational number. because both 9 and 16 are perfect squares. Okay, perfect squares. So the square root of 9, or they are square numbers, we call them. Okay. All right. So those are the solutions for the first activity. And that is just the classification of numbers. And if you look at it, it all comes from knowing this particular tree diagram here, as in the notes. Now, the next part of our work will be show that the following numbers are rational. How can we show that these numbers here are rational? So showing that these numbers are rational, we're going to convert from a recurring decimal now to rational. Now remember that this dot on top here, top of the number, that means it's a recurring decimal. Now what's a recurring decimal? A recurring decimal just means that that 1 is going to repeat itself indefinitely. So if I say like 0.1 recurring, it's actually equal to 0.11111. And that 1 will be non-terminating. So we can now put dot, dot, dot after that. 11111. Okay. So therefore, if I'm going to now show that the following numbers are rational, I need to firstly expand. I need to let x equals to 0. And I need to expand that like how I expanded it here. 0.111. You can write as many, expand as many, because it's going to expand infinitely. And you can put dot, dot, dot. So you're only going to consist of all ones here. That's going to repeat itself. Then, because you got one recurring decimal, so if you got one recurring decimal, then you're going to multiply by 10 for one recurring decimal. So for one recurring decimal, you multiply by 10. So you're going to call this equation 1, and then you're going to say equation 1 times 10. The equation 1 times 10 is going to be 10x equals 2. Now remember that when you multiply by 10, you have to move your comma one place to the right. So that becomes 1.11111. Also an infinite number of ones that's going to repeat itself. Okay? So when you multiply by 10, you move your comma one place to the right. So you've got two equations. Now if you subtract equation 2 minus equation 1, you are going to get 10x minus x is going to give you 9x. So 10x minus x is 9x equals 2. Now, when you subtract this part over here, if you look carefully, your recurring parts will be identical after the decimal. So therefore, the recurring parts now cancel themselves out. So you're only left with 1 minus 0. And 1 minus 0 is equal to 1. Okay, so therefore you'll get 1 and x. Now, if you solve for x, you'll get x equals to 1 over 9. The answer is 1 over 9, and we can check that using a calculator. We can put that there. 1 over 9 equals to 1 over 9 plus their decimals, and you'll see you'll get a recurring decimal of 1 there. Okay, so let's look at the next example. We want to show that 1.75 is also a rational number. We're going to try to convert it to a rational number using the same process. So for B, so we're going to let x equals to 1.75775, and we're going to call it equation 1. So here we've got two recurring decimals. The 7 and the 5 are both recurring, as you can see there. So two recurring decimals with 757575. So when you got two recurring decimals, then you need to multiply by 100. And so you can get the pattern now. If you've got 3 recurring decimals, you'll multiply by 1,000. So for each recurring decimal, you just add 1 0, what you're going to be multiplying. Either, so just simplify it. If it's 1 recurring decimal, you multiply by 10. If it's 2 recurring decimals, you multiply by 100. Okay? And remember, when we multiply by 100, we're going to move our comma 2 places to the right. So let's take equation 1. Multiply that by 100. So we'll get 100x equals to, move it 2 places to the right, and you'll get, and if we move it, we'll get 175.757575. And now we're going to call that equation 2. And similarly now, what we did in the first example, we're going to take equation 2 and subtract equation 1. And let's do that. So what we got here now? We've got 100x minus x. 100 apples minus 1 apple is 99 apples. So 99x equals 2. Once again, if you look here, the recurring parts will cancel each other out. The recurring parts cancel each other out because they're exactly the same. They're identical. So there's no more recurring part. They cancel. Okay, it's equal to 0 when I say cancel, right? 757575 minus 757575 is 0. But we're interested in this part here now. This part here. 175 minus 1 is 174. So you write here 174. Therefore, x equals to 174 divided by 99. Now let's check our answer, whether it makes sense. We always can check our answer using a calculator. So we've now got, let's look at that. 174 over 99 equals 2. That's a simplified version. And there we go. 1.757575 and so on. Okay, you can see the recurring decimals here. Okay, don't worry about that 8 there, right? So 174 over 99 is our solution. Okay, so just a quick recap. Take it from the top. We are dealing with the numbers system, and we've classified our numbers, and we are able to answer a question of this nature by using our theory or using our tree diagram here. Okay, so you're only taking down the solutions because you have the module, sent it to you. So let's move on after that. Example 3. Now with the example 3 now, they want us to find a rational number between 5 over 7 and 3 over 4. Let's see what we can do in this particular example. Before I move on to this particular example, I'm just thinking of another example, how I can test you in the exam with the theory that I just discussed about, right? So what if I had something like the square root of, I said let t equals to the square root of x minus 1 all over, let's say, x minus 2, right? And I can tell you, like, for example, for what value or values of x is t, and number 1, I can say undefined. Right? And let's say I gave you all these numbers here. You can choose from these numbers here. Minus 1, 0, 1, 2, 3, and so on, right? Okay, I'll only give you these numbers. So you must choose from those numbers there. For which values of x will this expression t be undefined? So the answer here will be, it will only be undefined when your denominator is equal to 0. So you can take this down, right? When that is equal to 0. And the only time that will equal to 0 when x is going to equal to 2, because 2 minus 2 is equal to 0. The answer for that one there will be x equals to 2. And then the second one will be, let's say, non-real. For what values of x will it be non-real? Now, This thing will only be non-real when I have underneath the square root sign if it's negative. So if I got a negative here, okay, the only time I'll have a negative here, remember 0 is allowed here underneath the square root sign. So this one here is allowed 1. If I have 1 minus 1, it's allowed because the square root of 0 will be 0. And 0 over anything is still going to be 0. So it's real. It's not non-real, right? Okay. But if I put 0 here, inside here, if I say 0, like for example, 0 minus 1, now that becomes non-real. Now be careful of the denominator as well, right? So we already know that it can't equal to 2. So the one answer will be 0 and other one will be minus 1. Right? Minus 1 will work in the denominator because you'll have minus 1 minus 2, which is minus 3. But it won't work on the top here because minus 1 is minus 2. Square root of minus 2 is non-real. So the answer on the here, you'll write this answer here, right? You'll say x equals to 0 and also minus 1. Let's write it like this here, or x equals to minus 1. Okay, 0 or minus 1. That will be non-real. Why? If you substitute, what you get? 0 minus 1 is minus 1, or minus 1 is minus 2. So once if I have anything that is negative underneath the square root sign, then that means now that is going to be non-real. Okay, now that is a very, very nice question for you to understand for this section. Okay, let's move on then. Here, we have 5 over 7 and 3 over 4. Okay, we want to find a rational number between 5 over 7 and 3 over 4. Now remember, rational is any number that can be expressed in the form a over b, where a and b are both integers, but b cannot equal to 0. Okay, that's an example of a rational number, q. So if we, okay, let's say that we want to multiply here by, we want to get a common denominator, right? So let's say we both, right, so we multiply 5 over 7 times 4 over 4. And that will equals to 5 times 4 is 20 over 28. Then if I say 3 over 4 times 7 over 7, and that now will equals to 3 times 7 is 21 over 28. But this is still not helping me because I want to find a rational number between 5 over 7 and 3 over 4. So what I can do is I can multiply it again. So let's multiply it one more time. So let's multiply this by 2 over 2, and let's multiply that by 2 over 2. So 20 times 2 is 40. 28 times 2 will give me 56. 21 times 2, that will be 42. And 28 times 2 is 56. So long as I got a common denominator here, I'm okay. Then I can just compare the numerators. That numerator is 40, that numerator is 42. Therefore, the number in between the two I can put as 41 over 56. And that should be my solution. 41 over 56. There you go. That's a rational number. Does it fit the criteria of a rational number? Yes. A over B. Q is for rational numbers, where A and B are integers. A and B are both integers, but we cannot have B must not equal to 0. So it fits the criteria of a rational number. Okay, so this is just basically covering the theory and the initial part of what we need to know. Now here, let's see. So what do we have here? We've got they're telling us here, between which two consecutive integers do the following irrational numbers lie? Now, we know that, see, these are all irrational numbers here. Square root of 12 minus the square root of 12. They're all non-recurring and non-terminating decimals here, okay? So here you got A, the square root of 12. The square root of 12. So if we look at square roots will be as follows. If you draw a number line, you can have the following square root. So you can basically look at, in your number line now, you're starting obviously from, let's say 0 there, 0 squared is 0, and let's go up here, 10 squared is 100. Now obviously that's too big, right? We don't need that. But if you go further down here, we can now see that if you have 1 squared will give us 1, 2 squared is 4, 3 squared is going to be 9. Okay, so 3 squared is 9, and then 4 squared is 16. So straight away now, if you look at it, 3 squared is 9, so the square root of 9 is 3. 4 squared is 16, so the square root of 16 is 4. Which means that in between here will be the square root of 12. So therefore, it's going to lie between these two integers. So we can now conclude that it will be between 3 and 4. Okay, we can check our answer using the calculator. For example, we can now say that the square root of 12 equals to, press the decimal, 3.464. 3.464. And you can see 3.464 is between 3 and 4. Okay. Let's look at the next example. B is minus the square root of 12. So remember now that it has to be minus the square root of 16. You can't have the minus sign inside of the square root sign. Then if you have minus 3, it has to be minus the square root of 9, like so. Okay, the minus sign have to be outside of the square root. So you can see now that minus the square root of 12 will be in between somewhere over here, minus the square root of 12. Okay, so minus the square root of 12 will lie between minus the square root of 16 and minus the square root of 9. So therefore, it must lie between minus 4 and minus 3.